All right. Good morning, true quantum enthusiasts. Thanks for coming. We're about ready to get into the final awesome algorithm in quantum computing, the factoring algorithm. That's what we're going to do in the last part of the class after Thanksgiving. Before we get there, we need the crucial subroutine that's going to make it all happen, which is this rotation estimation subroutine that we talked about a lot. And today we got to talk about one more time because it's still not quite strong enough to do what we're going to need it to do in the middle of factoring. So the factoring algorithm itself is a little bit complicated. There's some number theory going on. There's some interesting geometric ideas. There's some entanglement. So there's going to be a lot of stuff. So there's going to be a time when we're going to need to use rotation estimation right at the heart of it, and we'll already be deep into some tricky stuff. So we're really going to want it so that this rotation estimation, it's really just tied up in a neat package. We can just take it off the shelf, plug it in, and not worry about it. So today we got to get it into that perfect package form so that we can just use it and be happy with it. So you might think oh, we already worked so hard on it. It did a lot of stuff. It has the ability to estimate all the tons of digits of precision of a rotation. What more do you need? Well, there are a few things we can add to make it a little bit better and a little bit more convenient. So that's what we're going to do. So in order to describe that, I have to first kind of remind you of how the basic algorithm was working. And the setup from lecture 17. This is a good day to lecture about it too, because I know you happen to know it so well. You're just studying it so recently. I'll remind you what was going on in lecture 17. So the setup was, you had some unitary which acted as a mystery rotation. And the main setup we discussed was just when it was acting on one qubit. Now, we also talked about it a little bit in the context of Grover, and I'll get back to that. But let's just say for now it's acting on one qubit, so it's a mystery rotation R, acting as rotation by some mystery angle theta between 0 and 90 degrees. And your goal is to estimate theta to a lot of precision. And we talked about how we're going to try to estimate it to within thousands of digits of precision, which at first doesn't even seem to make sense, but it will. It will be possible. And part of the reason that it's going to be possible is that we're going to imagine that not just that you're given the ability to do R, but you can also do R to the power of 10, which remember means R repeated 10 times, and also R to the power of 100, and R to the power of 1,000, and R to the power of even 10 to the n. And normally if you just had the code for R and you wanted to do R to the power of 100, you just have to run R 100 times successively. And that's no good if you're going to try to run R 10 to the power of 1,000 times successively. But in the context of factoring, for some reason, we'll actually be able to get extremely efficient algorithms for doing the R that we care about as many times in a row as we want. Okay, so that's going to be the setup there. Okay, so with all this stuff, we need to remember some details of how the algorithm works. I won't go over all the details, but it'll be nice to remember some details of how the algorithm works. So here's a sketch of how the algorithm works. It goes in sort of stages. The 0th stage is about using R. The first stage is about using R to the 10. The second stage is about using R to the 100, and so forth. And okay, in the 0th stage, what do? You kind of want to get a few digits of precision in the first 0th stage. So you make a qubit in the state 0, you apply R, that rotates it by this mystery angle theta, and then you extract, you measure it, and you do this repeatedly C times. C is some big fixed constant, 100,000 or something, but some constant number of times. Okay, and that gives you roughly some estimate of, let's see, the probability that you would see the outcome 0 here is cos theta squared, and the probability you see the outcome 1 is sine theta squared. And either of those, if you knew them, you'd pretty much know theta. So technically the way we did it was we, let's say, counted the number of times we saw 1, or you could say not 0, and let q hat be this fraction of times that we saw 1, and then q hat is basically sine theta squared, so we just invert that. We compute the arcsine of square root q hat, and we're okay, this is our first guess for theta hat. And we saw that, maybe you make C to be 100,000 or something, and that's a pretty good guess. With overwhelming probability, like the first couple of digits are like bang on, they're super accurate, and even like maybe the third digit is like pretty accurate. I'm being a little bit informal here when I talk about like digits being accurate and like precision. Like the formal statement is like, oh, theta hat is it's within 0.0001 or whatever of theta. But I'm just going to informally talk about it as like digits being accurate. And then the trick was you're like, I'm going to do this all again, but with 10 theta in place of theta. And that kind of like shifts the decimal place by 1 and sort of lets you estimate like the next digits equally well, like digits 1 through 3 of 10 theta, which are like digits 2 through 4 of theta. So here you rely on the fact that you can do r to the 10, and you basically do this whole story again, and then you get like digits 2 to 3, like very accurate, and maybe the fact that this 2 overlaps with 2 here makes things check out, and you're like, oh, now I have full, I'm very confident about this digit, and I'm like pretty confident about digit 4. Again, it's like the more proper statement is like some statement about intervals, but this is the gist of it. And then you're like, great, now I'm going to try to get one more decimal place, so I'll do this whole story again with r to the 100, and get like another digit of accuracy, and so forth. And we do this like n times, and we get like n digits of accuracy for theta. Okay. That's the story. I now feel technically obligated to tell you about this like one annoyance that like kind of always makes it annoying. And last year when I taught this, I kind of glossed over this, and then like one student, it was a good student, he's like, I tried to like actually implement the factoring algorithm as you described it in class, and I kept getting like hung up on this issue in the rotation estimation. I was like, man. Okay, so I'm gonna like, really tell you this, even though don't stress about it too much. There was like one like little glitch here, if you remember, where we assumed the initial angle is between 0 and 90 degrees, and we needed that so that like there was a one-to-one map between q and theta. But then as you're doing this, like 10 theta and 100 theta and 1,000 theta might not be between 0 and 90 degrees. So at each of the subsequent stages, you have to, you more or less know where theta is, and you're like, man, I wish it was between 0 and 90, because then I could repeat this. So you're just like, I'll just like add an artificial offset to it of my own doing with my own rotation. That could be like one of these multiples of 45 degrees to put it into like 0 and 90, and then I'll estimate that, and then I'll undo that. Okay, so this glitch is going to like constantly annoy us, but I'll mention it occasionally. Okay, so great. You might say, this is pretty good. Like, what more could we possibly need? Couple things. First, it's going to be mediumly important later to observe that like this algorithm has a form that's maybe a little simpler than it looks. So what I want to say here is the way I've described it is like the algorithm like makes some qubits, does some unitaries, does some extraction, thinks a little bit about the answer, like does some classical computation, and then like does that all again, like makes some qubits, does some unitaries, does some extractions, thinks a little bit about the answer, and repeats that. And I just want to tell you now, you can reorganize it so it's like it makes all its qubits, then it does all its unitaries, then it does all its like measurements, and then it does all its classical computations. And I'll tell you this now, I'll sketch it, and it will be nice later for us to remember that it's okay to put it into this form. So ignoring the glitch, which again, like I'll mention briefly, here's like just an even further like bird's eye view of this algorithm. It'll be nice to have later. Basically, in step 0, we're going to like make new qubits. And I'm going to call them like D1, D2, DC. That's like some 100,000 qubits. And I'm going to call these like the data qubits, because we're going to like do this thing D times. So let's just like make C times. So let's make all C of these qubits first. That's fine. And then we're going to apply R to each of them. And then, then we're going to extract them all. And record the outcomes. And I'm going to, as I said, call these also like the data bits. Okay, and these are actually just a bunch of zeros and ones, and what we're eventually going to do is like count them, divide by c, take square root, arcsine. But let me just remember that like we're going to collect, like a constant amount of data here that we're going to think about later. Okay, and then like in stage 1, it's going to be kind of similar. We're going to like make even more qubits, dc plus 1 through d2c. And we're going to apply r to the 10 to each of these. We're going to extract all of them and get data bits dc plus 1 through d2c and so forth. I mean, similarly with r to the 100. Okay, and for like n stages. And let me just add that like at the end, there's a simple classical, by which I mean not quantum, I'll call data processing algorithm. That takes all the data bits, which is d1 up to like dc times n, I guess, and computes the final estimate of theta. Okay, so I'm just saying, like, instead of like figuring out your first 3 digits of precision for theta here, like computing the arcsine or whatever, and then computing another arcsine and a fraction and computing the digits, you could just like save up all the data like on a piece of paper and like do all your classical calculations at the end. Okay. And now I want to even look at this and reorganize it further. So here we like make a bunch of qubits, we make some more qubits, we make some more qubits. We could make all those qubits right at the very beginning, like all c times n qubits right at the very beginning. And then notice like, after we never like touch these qubits again after we extract them. So we could also do all the extracts at the end. Like we could make these qubits, apply r to each of them, and be like, I'll do this a little bit later. And then make some more qubits, apply r to the 10 to each of them, and then be like, I'll do this a little bit later, and so forth. Okay, so I'm really trying to get this into like the more normal form for quantum algorithms, where you like make all your qubits at the top, then do all your unitaries, then like just extract all at the very end. Okay, so I'm just trying to convince you that like, even though we didn't originally phrase it this way, we can write the algorithm in this like more normal looking way. So this is like the takeaway, and after I'm done with it, you might not think this is such a great punchline, but we're really going to want to like again put this in like the back of our minds so that when we get around to actually using this, it'll be like a nice black box that we can appeal to. So the takeaway is that the structure can look like this. Stage 1, just like make all your qubits, d1, d2, up to d, c, n. And then like do all your unitaries. Let's just say use the unitaries. R and r to the 10 and r to the 100 and so forth up to r to the 10 to the n. 3, now do like extract all. Well, let's just say extract all the d's. So measure all the d's and get like all the data bits and then like classically process the data bits. Okay, and I just want to get into this form because when we eventually use it, I want to use the fact that like it's really equivalent to just like add some new qubits, do some gigantically complicated, qubit manipulation, unitaries, and then do extract. Now, for the record, I'll mention, like, oh, what about the glitch? See, the glitch seems a little bit funny because the way I phrased the glitch, like after stage, let's say, 0, you kind of roughly know theta, and you're like, oh, theta is like right around, like, I don't know, like 179 degrees. So that's not between 0 and 90, so I'll like artificially rotate by 45 like a couple of times to make it between 0 and 90, and then I'll do it. So like the glitch has this like feeling that like, oh, you have to first look at the results in order to know what to do in stage 1. And that's contrary to what I like set up here. Here I was like, you know, it's going to be totally oblivious. You'll just like make these qubits, do these unitaries, do this extraction. You don't have to look at the results into the very end. You can get around it. You can still make it in this way. Just by like, here's a way to get around it. In stage 1, where you're like, oh, maybe I'll need to do an offset of 45 or 90 or 135. Just try all of those. I mean, there's only 8 of them. So just like do everything you're going to do like 8 times, one for each possible fixing offset. One of them is the correct one that you would use. And just do all of them. It'll, okay, make your work like 8 times longer. And then just leave it all to the very end. Just leave it to this classical data processing algorithm. When it's processing the data, it's like, oh, in stage 1, you should have rotated by 45 degrees. Well, luckily, I did all 8 possibilities, so the one that you needed is in there, and so forth. OK, so that's just to say that we can even take care of this. OK, so this was not the important this was not really the important upgrade or thoughts we needed to have on rotation estimation. But it'll nevertheless be nice to know that we can get it into this form.